So I'm going to talk about functional blocks. So these functional blocks are like building blocks, which are used in larger design. So this is the outline of this presentation. I'll talk about decoders, I'll talk about encoders, multiplexers, demultiplexers, and some design examples at the end. So the meaning of a functional block, it is a combinational circuit, and it can be implemented using normal gates, like we have been doing so far. However, we can use them to design large circuits. So these are very common. Okay, so they are very commonly used. They are very useful in design. So what we are going to study, okay, in this lecture, we are going to study blocks like decoders and multiplexers. And we are going to reuse these blocks, okay? These common blocks, we are going to reuse them in design. We can have them in the design library, okay? And we can test these blocks for correctness, and we can reuse them in different projects. In the past, people used integrated circuits. So they had like functional blocks were implemented like integrated circuits. And you can have like small scale integration. And it means that you can have like tens of gates on a single chip. That will be called small scale integration, SSI. Of course, as technology improved, people went into medium scale integration. It means that you can have hundreds of gates on a single chip. Then large scale integration. It means that you have thousands of gates. And then we have very large scale integration. It means that we can have hundreds of thousands, even millions of gates on a single chip. Today, you can even have billions of gates on a single chip. So the numbers have increased because technology has improved and the integration has increased. So you can actually have even more gates. So this is called like ultra large scale integration. Right. So the functional blocks that we are going to study in this presentation, we can actually have them as building blocks. We can put them in a design library. Like you have libraries in the case of software, you can also use libraries when you are designing hardware. And you can reuse the same blocks as components. You can use them in different projects. Right, so let me start first with the decoder. So what is a decoder? It's called a binary decoder. It is a combinational circuit. It has n inputs. So for example, we can number these inputs, okay? From, let us say, from 0 to n minus 1. These are my inputs. And then it has 2 to the power n outputs. So notice that the number of outputs is going to grow exponentially according to n. Yani for example, if we have 2 inputs, then the number of outputs will be 2 to the power 2, which is equal to 4 outputs. Like if I have 3 inputs, then how many outputs I will have? And if we increase n to 3 inputs, if you have n is equal to 3, yes?
8.
Exactly, I will have 8 outputs. If we have 4 inputs, then how many outputs?
16.
16, thank you very much. And if I have 10 inputs, then how many outputs I will have?
1024.
Excellent. 1024, because 2 to the power 10 is equal to 1024. So notice that the outputs is going to grow exponentially. Okay, so every time you add 1 input, then you see that the number of outputs is doubling. Okay, so this is why it is, and it is going to grow. Okay, so the size of the decoder becomes very large if you increase n. Now, the nice thing about the one important feature about the decoder is that only one output is set to logic 1, and all the remaining outputs are zeros. So that's what the decoder does. It's going to produce 2 to the power n outputs. All of them are zeros except 1. only one of the outputs will be equal to 1. And this conversion between input and output is called decoding. Look at some examples of decoders. Okay, let us start with a small decoder. Okay, let us say we have here a 2 to 4 decoder. Now notice that my inputs here, we can number them. Now we can start at the most significant bit. Now it's called binary decoder because the input appears in binary. So here A1 is my most significant bit and A0 is my least significant bit. So these can be connected to inputs 0 and 1 respectively. We have 4 outputs. We can number them from 0 to 3. So this is output 0, this is output 1, and this is output 3. So we can call them D0, D1, D2, and D3. Okay? So these are my outputs. Now the decoder is nothing but a combinational circuit. And therefore we can draw a truth table, okay, for the decoder. Notice that the inputs here can be 0, 0, 0, 1, 1, 0, and 1, 1. These are the 4 possible combinations. And therefore, you get only one of the outputs is equal to 1. So this is the truth table. And you can see the 1 appears along the diagonal. So if the input is 0, 0, you get D0 is equal to 1. If it is 0, 1, you get D1 is equal to 1. And if it is 1, 1, you get D3 is equal to 1. So when you look at the input in binary as if it is actually a binary number. And when you convert it from binary to decimal, you know that exactly which one of these outputs must be equal to 1. So that's the truth table. Now let us take a look here at a 3 to 8 decoder. So this is another example of 3 to 8 decoder. It has 3 inputs. Now notice that how I'm naming these inputs. A2, A1, A0. So the most significant bit here is bit 2, and the least significant bit is bit 0. So you can have 8 possible combinations from 0, 0, 0 to 1, 1, 1. So these are 8 entries in the truth table. So if the input is 0, 0, 0, it means that D0 must be equal to 1. And if it is 1, 1, 1, then it must be D7 must be equal to 1. Okay? Because 1, 1, 1, if you convert it to decimal, you will get 7. So therefore, only output D7 will be equal to 1. Now you can pick any entry. For example, 1, 0, 0. Okay? 1, 0, 0, it means 4. So therefore, D4 must be equal to 1. So notice that all the ones here appear on the diagonal, and all the remaining outputs are zeros. This is the decoder. That's what the decoder does. Okay, so this is the function of the decoder. Okay, so so these are examples of binary decoders. Do you have any question about this? Is this clear? Right. So now you might actually ask, how is this useful? Yani, how can I use a decoder? Before I talk about the use of the decoder, let us just spend a few minutes talking about the implementation of the decoder. So let us take a look here at a small decoder, okay, a 2 to 4 decoder. This is the truth table. Okay, we have seen the truth table in the previous slide. Now the decoder can be implemented easily using gates. So notice that each output of a decoder is a minterm. Okay, so each output is a minterm, and I can write an expression, okay, for each output. So D0 will be A1 prime, A0 prime. It means that D0 is equal to 1 only in one case, when A1 equal to 0 and A0 equal to 0. Whereas D3 is equal to A1 and A0, indicating that D3 is equal to 1 only in one case, when you have A1 equal to 1 and A0 is equal to 1. So in order to implement the decoder, I need AND gates. So these are AND gates. I need an AND gate for each output. And I need here 2 inverters to invert the inputs. So some AND gates will use, for example, the inverted inputs. And this will be A1 prime, and this will be A0 prime. Okay, so we use the output of the inverters as inputs to the AND gates, and some of them will not use the inverted inputs and just use the inputs directly, the true value of the input. So that's a 2 to 4 decoder. If I would like to implement a 3 to 8 decoder, I will need 8 AND gates, and I will need 3 inverters because I need to invert all my inputs, and you can see that each output here is a minterm. Each one of these outputs is a minterm. Okay, so for example, pick any output, like for example D4. So D4 means 1 0 0, so we write it as A2 A1 prime A0 prime. Okay, so that's D4. So think about here the output as a minterm, and you can easily obtain the equation, and you can easily implement the decoder. So that's the implementation of the decoder. I'm going to show you how we can use decoders to implement functions. Now you say that, okay, now I understand decoders. Okay, so what is the use of the decoder? Now, we have seen in the previous slide that the decoder is going to generate all the minterms because we have actually one output for each minterm. And we know that any Boolean expression can be expressed as a sum of minterms. We already have studied this at the beginning of the semester. So therefore, we can actually use the decoder to implement any Boolean function. In fact, there is no need to minimize, okay, the Boolean function. You can just look at the truth table and implement it directly. Now you can implement it directly using a decoder, but you need extra gate. Yani for example, you can use an OR gate. Let me give you an example. Suppose I would like to implement a full adder. Now the full adder has 3 inputs, A, B, C, and it has 2 outputs, the carry out and the sum. So these are the 2 outputs, and these are given by these 2 columns. So here, this is my function C out, and this is here my output or the function sum. So basically, each output is a function. Now we can look at the minterms. Yani for example, in the case of sum, we have this is a minterm, which is minterm 1, this is minterm 2, this is 4, and this is 7. So we can write this in sigma notation. And also we have C out. This is actually minterm 3. This is 5. This is 6 and 7. And we can write this also in sigma notation. So we know what are the minterms, okay, for sum and the minterms for C out. Now we can implement C out and sum, okay, using one decoder. I can actually produce all the minterms of the full adder, and I need 2 extra OR gates. So here's an implementation of the full adder. I can use a 3 to 8 decoder. Now notice that A is the most significant bit, is connected to input 2. And C is the least significant bit, which is connected to bit 0. So now ABC can be from 0, 0, 0 all the way to 1, 1, 1. Now notice that for sum, I need 1, 2, 4, and 7. So therefore, look at the output D1, look at D2, look at D4 and D7, and connect them to this 4-input OR gate. So we simply take the ORing of these 4 minterms and we get the output sum. That's so simple and so easy. If I would like to get C out, now C out here is a 3, 5, 6, and 7. So look at 3 here. This is 5, this is 6, and this is 7, and connect them to C out to this OR gate, and the output will be C out. Okay, so we use one decoder, okay, with 2 OR gates. So we can have, let us say, a combinational circuit that has multiple outputs. All what we need is just one decoder. And we need an OR gate for each output. That's one use of the decoder. We can use it to implement any Boolean function like this. Remember the implementation of the full adder? We used like 2 XOR gates and 2 AND gates and 1 OR gate. But now I'm using a 3 to 8 decoder and 2 OR gates. That's another way to implement the full adder using a decoder. Now you only need one decoder, okay, to generate all the minterms, and this decoder can be shared by the two outputs, the sum and the cout. You don't need two decoders, only one decoder, but you need one OR gate for sum and another OR gate for cout. And these are 4 input OR gates because we have 4 minterms. 4 minterms for sum and 4 minterms for cout. Okay, you see how simple it is. Do you have any question about this? If you have any question, you can interrupt me or you can raise your hand, and I will be glad to answer your questions. طيب. So this is one way to use decoders, is that we can use them to implement functions. Let us continue. Here's another example. Now, sometimes you might actually have a function that has many minterms, and you might actually have a large number of minterms, but only few max terms. Let us take a look at this example. Now, notice that here we have a function. We have actually here the truth table, in fact, of a circuit that has 3 outputs. So we have output F, we have output G, and we have output H. So we have 3 outputs. Now, all what I need is just one decoder to produce these 3 outputs. Notice that for the function F, we have here 1 minterm, I have a second minterm, and the third minterm. So only 3 minterms. So therefore, if you have 3 minterms, what does it mean? What does it mean to have only 3 minterms? And in the implementation, I can use a 3-input OR gate. And if you recall from the last example, because we had 4 minterms for sum, we had to use a 4-input OR gate. But here we only have 3 minterms for the function F. Just look at the column here for the function F. So because we have only 3 ones in this column, it means that I need only a 3-input OR gate type. Now look at the function G. If you look at the function G, you can see that there are 6 ones in this column. There are 6 minterms. So therefore, you need a wider OR gate. You need a 6-input OR gate. So you need actually a wider OR gate because we have 6 ones. However, you can look at the zeros. You have here 2 max terms only. So you have 2 zeros. So rather than generating all the ones, okay, and using a 6-input OR gate, we can use a NOR gate. So the NOR gate can be used to produce the zeros of the function, not the ones. So therefore, the NOR gate, if you have a fewer number of max terms, so we count the zeros in the column. If you have fewer number of zeros, it means that fewer max terms than the minterms, then it will be better to use a NOR gate, because the NOR gate, its output is inverted. And because the output is inverted, it can produce a 0 rather than producing a 1. Now, this will be simpler. We can reduce the cost of the implementation by using NOR gate when we would like to implement max terms, when you have fewer number of max terms. In the case of the function H, you only have 2 ones, so a 2-input OR gate will be sufficient. So now what we can do is that we can draw the circuit like this. This will be a 3 to 8 decoder. Notice that the inputs here are A, B, C. These are connected to input 2, 1, and 0. So A here is the most significant bit. It's actually bit 2. So A, B, C can be from 0, 0, 0 to 1, 1, 1. Now, in the case of the function F, I need to focus here on the minterms of the function F. So these are given in sigma notation, okay, as minterm 2. This is minterm 2, 5, and 6. So I can actually connect them to an OR gate, a 3-input OR gate, and this will output the function F for me. Okay, that's actually here is a 3-input OR gate that will output the function F. In the case of the function G, I can use a 6-input OR gate because we have 6 minterms. But rather than using a 6-input OR gate that will be expensive because it has 6 inputs, so the fan-in is large, we can use only a 2-input NOR gate because we only have 2 zeros. Notice that we only have 2 max terms. So we have max term. I can write the max terms in pi notation. So we have 3 and 6. So we can focus here on D3 and D6, and we can connect them to this 2-input NOR gate. So 2-input NOR gate is much smaller than a 6-input OR gate. So if you have here D3 is equal to 1 or D6 is equal to 1, any one of these is equal to 1, you get the output equal to 0, because in the case of the NOR gate, it is sufficient that one of the inputs is equal to 1 to get the output equal to 0. So you see that the NOR gate can output the max terms of the function. So that actually is much better than using an OR gate that will output the min terms. So here you can see that the max terms are 3 and 6. So therefore, we can use the 2-input NOR gate to output 0. Okay. Finally, for the function h, that would be very easy because we only have 2 min terms, 0 and 5. So we connect D0 and D5 to this 2-input OR gate, and we are done. So we are sharing the 3 to 8 decoder, okay, by the 3 outputs. I only need 1 decoder, regardless of the number of outputs. But then I need extra additional gates to output each function. Okay. Any question about this? So this is really the idea of using decoders. We can actually use them to implement any function. In fact, decoders are used a lot, okay, in the design of digital circuits. They are used, for example, to implement memories today. Inside the memory of a computer system, people actually use decoders. Okay, so they have actually, they are very useful in the design of large circuits. Any questions about this? Do you have any exam today or during this week? Do you have exams? Because you are very focused. Do you have an exam this week?
Yes.
Okay, good. I mean, it's not good. It's something that you have actually to deal with. But
Yes.
focus on this. It's just actually a small lecture, short lecture. Focus on it and actually raise questions. Okay, that way you can actually understand better the material. Okay, so it's better to understand it now. Okay, let us move on. Now let me show you another type of a decoder. So this is a decoder with enable input. Okay, so we can add an extra input, which is called enable, to a decoder. So this is like this is the same as the decoder that we have seen before, but we have added an extra input. Now this extra input is useful if you would like to disable a decoder. Now the meaning of disabling the decoder means that we would like to have all the outputs to be zeros. Remember that the decoder that we have seen before is that exactly one of the outputs is equal to 1 and the remaining outputs are zeros. But suppose that in a given design, I would like to have all the outputs to be zeros. So I can use an extra enable input. So if enable equal to 0, I don't even care about these inputs A1 and A0. So I put actually here don't care in the inputs. So it does not really matter what's my input A1 and A0. It could be 0, 0, 0, 1, 1, 0, 1, 1. It does not really matter. All the outputs will be zeros. That's because enable equal to 0. So enable equal to 0, it means that the decoder is disabled, and therefore all the outputs are zeros. If enable is equal to 1, then one of the outputs will be equal to 1 according to the inputs A1 and A0. So that will be the typical decoder that we have seen before. But now you can see the importance of enable because we can disable the decoder and we can have all the outputs to be zeros. Now, how do we implement a decoder that has an enable input? That will be simple. Rather than using here, let us say 2 input AND gates, we use 3 input AND gates. 3 input AND gates, and we connect the enable input, to the AND gate. So these AND gates have an enable input, and you can see that enable now is part of the equation. So if enable equal to 0, you get all of them zeros because enable is part of the equation. If enable is equal to 1, you get one of the outputs is equal to 1. So rather than having a 2 input AND gate for the outputs, D0, D1, D2, D3, we use an extra input to the AND gate. So basically we end with the enable input. So if enable equal to 0, we get all the outputs are zeros at the same time. Like, is this useful? Well, it turns out that having an extra enable input is useful. Yes, it is very useful. Now let me show you how we can build a large decoder using a smaller decoder. So this will be a hierarchical decoder. So we are using a small decoder to build a larger one. I'm going to show you 2 examples. One example is shown in this slide, and I have a second example which is shown in the next slide. So in this slide, I would like to implement a 3 to 8 decoder using 2 smaller 2 to 4 decoders with enable inputs. And also I'm going to use an inverter here. Now having an inverter here, can be used to implement a 1 to 2 decoder. So let me explain this. So we have 3 inputs here, A2, A1, A0. Right. If A2 equal to 0, if this is equal to 0, then the output of the inverter will be equal to 1. So the top decoder is enabled and the bottom decoder will be disabled. So if the bottom decoder is disabled, we get D4, D5, D6, D7, we get all of them to be zeros. Now the top decoder is enabled. We're connecting A1, A0 to input 1 and 0 here. So therefore you get one of the outputs is equal to 1. So either D0, D1, D2, D3, one of them will be equal to 1 and all the other ones will be zeros. Notice that D4, D5, D6, D7, they are all zeros. Now that's if A0 is equal to 0. So we are enabling the top decoder and we are disabling the bottom decoder. So for this reason, you have D4 through D7 are all zeros. Now, suppose that we reverse this. We make A2 equal to 1. So now this is inverted, so this becomes 0. And this is the same thing here as connecting A2 directly here to the bottom decoder. So we are disabling the top decoder and we are enabling the bottom one. That's when A2 is equal to 1. So that's actually shown here. So notice that if A2 is equal to 1, the top decoder will be disabled. So all of these will be zeros. While here you have one of the outputs, D4, D5, D6, D7, one of these outputs will be equal to 1. So D0 through D3 will be all zeros, and one of the outputs, D4 to D7, will be equal to 1. So now what we have done is that we have used 2 small decoders, a top one and a bottom one, which are 2 to 4, to implement a large decoder, which is a 3 to 8. But notice that we have used here the enable input to enable one of them and to disable the other one. So notice that here we have, notice the ones here along the diagonal, and you have only one of the outputs is equal to 1, and all the remaining outputs are zeros. So this is a 3 to 8 decoder. Now notice that this inverter, which is shown here, we can use it to implement a 1 to 2 decoder. Because if this is 1, you get this output equal to 0 and this output equal to 1. And if you reverse it, you get basically the other outputs. So this is like a small 1-to-2 decoder implemented using just a single inverter. So it has one input and two outputs, and there is only a single inverter inside. So that's a 1-to-2 decoder. Questions about this?
Teacher.
Yes, تفضل سعد.
نقدر نختصر الجدول ذا بأن نحط وحدات تحت بعض ونخلي الدي 0 ودي 1 ودي 2 على اليمين ولا؟
Well, remember that okay, only one of them is equal to 1.
ايوه فاهم عليك بس انا يعني من باب اختصار
according to 3 inputs.
ايوه فاهم عليك بس انا بخليهم تحت بعض يعني مثلا كلهم يكونون
you see that
فوق
actually
وخليها
D0
جنب
is
كل واحد.
This is D0. This is D1.
فاهم عليك دكتور بس انا عشان ابى اختصر فهمت علي؟ ينفع؟
كيف تختصر؟
ابى اخلي الوحدات تحت بعض يعني واحد تحت
الدي
0 هذه كلها
هنا يعني
ايوه.
It does not make sense because if you put the ones one after the other, it will be the ones actually for the same output.
ايوه بس اصبر علي دكتور دقيقه شوي ابى اخلي الدي 0 على اليمين والدي 1 تحته وكذا ينفع؟
دي 0 على اليمين؟
اي دي 0 دي 1 دي وانا نازل كذا علشان يعني احدد ان الواحد هذا للدي 0 والواحد الثاني للدي 1 وانا
Remember this is a truth table. What we are drawing here is a truth table. What you are saying is not really a truth table. So this is a truth table that shows the outputs okay for every possible input combination.
تمام طيب.
I'm not sure actually if I understood actually what you are saying. So we are actually showing all the outputs for a given input. Okay. Now you would like to say that this is actually D0 equal to, so what I understood from you is that you would like to say that D0 here, it's actually already crowded. So let me clean it up and see if I understood your question. So what you want to say is that you would like to say that here D0 is equal to 1. You would like to say that D1 is equal to 1, right? That's what you wanted to say, Saud, right?
Yes,
okay, what about the remaining outputs? You have to indicate what are their values. You have to say that actually all the remaining outputs are all zeros. So for this reason, we don't write it like this. We show columns for D0, D1. This is actually as a circuit, يعني بالنهاية, all right? So we have to show all the outputs, okay? Not only one output, D0 or D1, you have to show all of them. So you have to indicate that actually which output is a 1 and which ones are zeros. Right. But your logic is correct. Yes, your logic is correct, but this is basically how we draw it as a truth table. Now, let me show you another example about how we can build a larger decoder. I'm going to build a 4-to-16 decoder. Now, that's actually be a much larger decoder. In the case of a 4-to-16 decoder, we have 4 inputs, A3, A2, A1, A0. Okay, and we have 16 outputs from D0 to D15, okay? So these actually are my 16 outputs. Only one of them should be 1 and all the other ones should be zeros. But I'm going to use now small 2 to 4 decoders to build this large 4-to-16 decoders. Now notice that I'm using here enable inputs, okay? Now this is very important because I would like to enable one of them and disable all the other ones. You can also have an enable input here, okay, for the top decoder. So basically we have 5 decoders in total. So one of them, okay, which is basically its inputs are A3 and A2. So depending on A3 and A2. So for example, if you have here A3, A2 are 0, 0, you get this output is equal to 1 and all the other ones are zeros. So this will be enabled while the other ones will be all disabled. So we are going to enable the top decoder, and therefore we have here D0, D1, D2, D3. One of their outputs will be equal to 1 according to A1 and A0. If you have it 0, 1, so let me write here, for example, 0, 1. Let me change this and put 1. So now this becomes 0. This becomes 1. So you get 0, 1, 0, 0. This will be enabled. This will be disabled, and therefore we are going to enable decoder 1, and one of these outputs, D4 to D7, will be equal to 1, and all the other outputs will be zeros, and so on.
Teacher, this decoder on the left works like a multiplexer.
It's not called a multiplexer. It is a decoder. Okay, it's not a multiplexer. A multiplexer means something else. I'll talk about multiplexers in another lecture. Okay, maybe next time. But this is not a multiplexer. This is a decoder. So let us not really confuse things, because multiplexers is something which is different. Okay, so this is decoder, not multiplexer. Now notice that this decoder here, which is shown, has also an enable input. And if this enable equal to 0, you get all of these are zeros, and all of them will be disabled, and all the outputs from D0 to D15 will be all zeros. Yani you can actually have all the outputs to be zeros if this enable equal to 0, you are disabling, okay, all the decoders and producing 0 outputs. Okay, so that's actually is a large decoder which is built hierarchically using small decoders. So I'm using a small decoder. So I'm using here 5 decoders, 2 to 4. It has 2 inputs, 4 outputs with enable input. So I'm using 5 of them to build a large decoder with enable. Okay, you might be asked in an exam to draw such a decoder or in a quiz. So you should be able to actually build large decoder using smaller ones. Okay, is this clear? Right. Let me show you a nice example. Remember the BCD to 7 segment decoder? Now the BCD to 7 segment decoder is a special type of a decoder. It's also called a decoder, but it's not a binary decoder. Now the BCD to 7 segment decoder, the input here, it has 4 inputs. So I'm calling here the inputs I3, I2, I1, I0. That's my BCD input. So this is the BCD. And it has 7 outputs, okay, because we have 7 segments in the display. So we can control that which segment should be turned on and which segment should be turned off. Now, if the inputs here is not BCD, and it's from 10 to 15, I can force all the outputs to be zeros. I can turn off my display. Okay, so if the input is not BCD, we can turn off all these segments, and therefore nothing will appear on the display. Now, we have seen this example when I talked about combinational circuit design. So we used 7 different Carnot maps, we obtained equations, and we started to extract the common sub-expressions and to implement the circuit, okay, for this BCD to 7 segment decoder. But this took us some time. I'm going to show you another way to design or implement this BCD to 7 segment decoder using a binary decoder and plus few extra gates. So let us take a look. First, let us take a look at the truth table. So the truth table is already given to us, or it's actually, we understand the truth table because we know that from each input that which segment should be turned on and which one should be turned off. For example, if the input is 0, 0, 0, 0, I would like to display the digit 0. So all these segments will be on except for G. G will be 0. So that will display the digit 0. And if you have 1, 0, 0, 1, then all of them will be 1 except for one segment, and this will be segment E. So this is segment E here, it will be off. Okay, I'm not going to turn it on. In the case of 8, when the input is 1, 0, 0, 0, I would like to turn on all the segments, and this will display digit 8 on the screen. Right, so this is the truth table. So we have the truth table now. Now we would like to implement. We would like to implement the BCD to 7 segment decoder. How am I going to do this? Well, this is easy. Okay, we can actually implement it using a binary decoder plus additional gates. Now we have a choice, okay, how to implement this. I can implement the min-terms, okay, using OR gates, or I can implement the max terms, the zeros, okay, using NOR gate. Now look at each output. Yani for example, focus on output A. Okay, let us take a look here at output A. So for this output here, A, just surround it. We have, this is one max term, two max terms, three max terms. So we only need a 3 input NOR gate. Now I'm treating here the inputs from 10 to 15. This is not BCD. So anything from 10 to 15 is not BCD. I would like to have the output here to be 0. So in the case of output A, rather than using a large OR gate that has many inputs to implement the ones, the minterms, I can actually focus on the zeros of the function and use a 3-input NOR gate. That will be a lot easier. The same thing can be said for the output B. Notice that we have these 3 zeros. The same thing can be said for the output C. We only have 2 zeros, so a 2-input NOR gate, and so on. Now, except for the output E, if you look at E, we have 1, 2, 3, 4 minterms. So we have less number of minterms. So I can use a 4-input OR gate to implement the output E. So we can actually have some of the outputs can use NOR gates and some of them can use OR gate. In fact, only E needs actually an OR gate, a 4-input OR gate. And all of them, we can focus on the zeros because we have fewer zeros than ones inside the truth table. Right. So now, okay, I need a decoder. Now this decoder will be a binary decoder, but we don't really have to actually go, it will be it will have 4 input, but rather than having 16 output, in fact, I can stop at output 9. So I'm going to use a 4 to 10 binary decoder. So there is no need here for having outputs 10 to 15 because I don't really need them, okay? Because my input here is BCD. Now I can easily detect if my input is greater than 9 with a simple logic. So I can detect here if the input is greater than 9 with a simple logic. Let me just clean up, okay, my writing. So to detect if my input is greater than 9, well, first we have to have I3 is equal to 1. I3 is the most significant bit. So if I3 is equal to 1, then we know that the input is greater than or equal to 8. Yeah, it's 8, 9, 10, and so on. So this will give me I3 is equal to 1. If I have I2 or I1 is equal to 1, it means that my input is greater than or equal to 10. If I1 is equal to 1, yani for example, if you have 1, 0, 1, 0, yani you have 1, here you have 0, 1, 0, this will be 10. So this will give me I3 equal to 1 and I1 is equal to 1. If you have, let us say, 1, 1, 0, 0, it means actually 12, 13, 14, or 15. So you have here I3, I2 is equal to 1. So this simple equation here that we have here, okay, can detect if the input is greater than 9. So rather than using a larger 4 to 16 binary decoder, we can simplify the logic by just writing a simple expression here. Just one OR gate that will OR I2 or I1 and one AND gate, and the output indicates that the input is greater than 9. So this equation is easy, can be obtained easily. We can obtain it even with the help of a Carnot map, if you want. This indicates that my input is greater than 9, yani from 10 to 15. So this will be for the last row. Okay, so that will indicate that my input is not BCD. Right. Let us implement here, for example, the output A. Now for the output A, I need actually to focus on these 3 zeros. Okay, so this is actually here is output 1. Okay, this is here 4. This is 4, and we have anything which is greater than 9. So we connect these two. So we take the output of the decoder. So this is output 1 of the decoder. This is output 4 of the decoder, and anything which is greater than 9 will give me the output A equal to 0. So we use here a 3-input NOR gate. If we look at E, so we have here 4 minterms. So we focus on the ones. I'm using a 4-input OR gate. So here we have 0. Okay. Here I have 2. So notice that how 0 is connected to the output E to this OR gate. We have 2, we have 6, and we have 8. So we connect them actually to this 4 input OR gate, and we get the output E. So you see that one decoder, just one decoder, plus few extra gates, we can implement a BCD to 7-segment decoder without going into the details how we need actually Carnot maps, minimize equations, and extract the common sub-expressions or terms, okay, to minimize the logic. We can do it very easily. So we use a 4 to 10 binary decoder to implement a BCD to 7-segment decoder. So the BCD to 7-segment decoder is a special type of a decoder. But it was also implemented using a 4 to 10 binary decoder plus some extra gates. Do you have any question about this example? So this is a nice example about how we can use decoder to implement combinational circuits. Now, there is a special type of a decoder that has inverted outputs. I'm going to skip this slide. So we call it actually here NAND decoders. So what we have seen before is that we have seen the AND decoders because we use actually the AND gates to produce the outputs. But you can actually have inverted outputs. Notice that here that the output is inverted. There is actually a small bubble at the output. So therefore, you get the output equal to 0, not 1. So only one of the outputs equal to 0, and all the remaining ones are 1s. And if it is actually disabled, so if enable equal to 1, we are disabling it, and therefore all the outputs will be 1s. So notice that enable itself is inverted. Okay? And we can actually implement it using NAND gates. And this is basically the equations. Okay, so this is called a NAND. This is a decoder that has inverted outputs, and we have implemented it using NAND gates. Now, that's actually an interesting type of a decoder. Okay, you can actually have this type of decoder. So here the output is complemented. Okay, whereas there the output is not complemented. So it's actually this will be, and you have to twist the logic. You have actually to think that the output now is complemented. So rather than having the output as 1, you have the output as 0. Only one of the outputs is 0. You can also implement, okay, functions using this NAND decoder that has inverted outputs. So rather than using OR and NOR gates, we can use actually NAND and AND gates to implement the function. Again, this is a twist, okay? So that's actually a twist of the logic because we look actually when the output is 0, not when the output is 1. So we can use NAND gates and AND gates. So the AND gates can be used, for example, to implement the zeros, whereas, for example, here for the function g, you have 2 zeros. So we use actually here an AND gate. So this actually we got 0 here, or we get 0 here. So in the case of 0, 1, 1, or you have 1, 1, 0, so that's actually the 0 here. You get the output equal to 0. In the case of the NAND gate, it will give you 1. Because it's going to invert it again. So that's a twist, okay? So that's actually called actually decoder with inverted outputs, or actually called NAND decoders. I'm going to skip this, okay? But this is actually something which is good to understand. So that's it for today, okay? Inshallah, in my next lecture, I need to talk about encoders. I need to talk about multiplexers and demultiplexers. I'm going to show you some design examples. So this might take actually more than one lecture.